So you can say save results with the set saving to true. You should have by the end of this. Let me just finish this. But you should have also this PDFs. It's not opening here. I'm just going to export. Probably my path has some forbidden character. That's why I cannot open through the RStudio. But then you're going to have this plot that summarizes the results. It's going to give you the motif, the odds ratio, the odds ratio calculated, and then the lower and the upper odds ratio with a 95% correction interval, confidence interval, sorry, and the number of probes in each enriched motif. So we can see that GATA4, GATA6, H, and 4A were the most enriched motifs. That's basically what I want to say. Normally, we take a look on the top ones, okay, in our results. Those are the most important ones. So where I did this, yeah, we can also, instead of getting the results ready, you can get that plot using the motif enrichment plot. Just give the results. So after you run the function, you should have this file. So you set this file as input, and then just say which are the cutoffs, like this, and if you want this summary here or not, and if you want to save this table or not. And the next step is, okay, now we have our enriched motifs, which is the mass regular transcription factor binding there. And yeah, just to show the results, this is what you have. You're going to have. So you have a list of enriched motifs, and for each one you have the probes associated with it. Okay. Yeah, that's basically that. So if we say length, just to show we have 203 probes associated with that enriched motif. So those are hypomethylated, and they have a target gene in the adenocarcinoma samples. Okay, so the last step is the TF get transcription factors. So again, give the data, the groups you are using, the mode, the direction. If you want to save the results in a CSV file, and if you want to save the plots or the ranking plots, you give the enriched motifs, and that's the main arguments. It's also important to say in R, if you have a doubt about the functions and which are the arguments, you can simply type question mark in the name of the function, and then you should have all the description of the function, the arguments, what they're expecting, an example, and etc. So you can run and see the results. There is also the vignette of the packages if you go to Bioconductor. So while it's executing, let's just, if you write Bioconductor ELMER, and then you open the manual, then you have a more detailed manual explaining step by step, like give an example how to create the data input, which I didn't cover on this workshop, but it's mainly created by this function, create my, where you give the gene expression, the methylation, platform, and genome you want. Yeah, basically it's that, and then you can go through all the steps I explained here. Just to show the paired ones. Yeah, so there is like the text that was used in both papers, some of the figures, and then explanation and references at the end. So it's going to plot this. So now imagine that I'm going to get just the first line of results. So we remember our most enriched motif was GATA4, and then we ranked the transcription factors. This is the ranking of all the 5 top percent. So we rank like all human transcription factors, and then we ask, okay, which is the most enriched motif that we know that has the similar binding motif, and that's classified by the family type. So this is given by the transcription factor class database, or you can also see that on Hokomoko. But let me see if we can open here, or Hokomoko. Yeah, so we have this classification of transcription factors. Let's see. And it classifies into family and subfamily. So these are the family, and then you open, you should have the subfamily inside it. Okay, so this is the subfamilies it has. And just to show, if you go to Hokomoko, you can see the ones that have similar binding motif. So here are the transcription factor family. Let me get one here as soon as the table is rendered. Yeah, let's get maybe the Hawks family. I think it's going to be good. Yeah, so if you want the Hawks family, you can also show the subfamily here. So you can see the subfamilies here. Let's sort by subfamily. So the first ones are on the same subfamily, and we can see they have like similar binding motifs. So a TT here, an A here, somehow a T here, and the other subfamilies, they have a little bit different ones. So normally, if you want to be like more specific, we work with subfamilies. So you can see that Hawks 913 has a pretty similar one, and it doesn't have like a G in the beginning like the BDX one. So normally we work with the subfamily if you want to be more stringent. Some cases it's better to work with the family, but it might be better to take a look on the binding motifs just to be sure which would be the case for each transcription factor. And then we rank them. So let's open this plot. So it's GATA4, and then so this ranking again. So this ranking is given by the correlation between the transcription factor expression and the mean methylation of those probes. And yeah, for the supervised mode, the ranking should be almost the same for all transcription factors, but for the unsupervised, that should change. So these are the ranking. We can see that for GATA4 motif, on the 5 top percent, we have GATA4 and GATA6. And the top one is GATA6. That's basically what it means. So you can just access the list, and let me just get the first 4 rows and first 4 columns, and then you should have the list of our master regulators here. So basically that what ELMER covers, and the next step would be to summarize several results, which I'm going to show in another video.